Hello everyone and I welcome you all to Study Room. So today we will be studying chapter 10 of class 9, that is gravitation. So let's get started. So have you ever wondered why do the objects drop from a height fall towards the earth? Why do the planets go around the sun? Or why does the moon revolve around the earth? So there is one answer for all your questions. It is due to gravity. And we're learning all about gravitation in this chapter. So let's watch this video.
Hey Globey, you ever wonder what keeps satellites like the International Space Station and the Space Shuttle in orbit? Once they get to a certain place in space, they just keep going round and round the Earth. But I also know about inertia. Moving objects have a tendency to move in a straight line. So what keeps them from just flying off into space? Oops. Well, it turns out that there is a balance between inertia and gravity acting on these satellites. Now we all know that gravity is the attraction between objects. How big that attraction is depends on the mass of the objects, or how big they are, and how far away the objects are from each other. Objects on or near Earth are caught in this attraction and are pulled down towards Earth's surface. So even if you throw a ball up in the air, gravity pulls the ball back down to the ground. But in space, all that seems to change. I'm sure you've seen pictures of astronauts floating around inside the space shuttle, and we all know astronauts don't float around here on Earth. So does that mean there's no gravity once the astronauts get in orbit? And what about way out there in outer space? Is gravity still important out there? Actually, gravity is still at work, even as far away as outer space. So what do you think keeps the space station or space shuttle from floating away into deep space? You got it.
So, history of gravitation. So when Newton was sitting under a tree, an apple fell on him. The fall of the apple made Newton start thinking. Each point of its orbit, the moon, fall towards the earth instead of going off in a straight line. So it must be attracted by the earth. So this is how Newton sir discovered gravitation. So let's do a small activity with a stone and a thread. So take a thread, tie a stone onto it and just revolve it. Okay, just like this person is doing. So you can also try. So what is the result you see? That before the thread is released, the stone tends to move in a circular motion with a certain speed and changes direction at every instant. Once the stone is released, it flies off along a straight line. This straight line will be a tangent to the circular path. Once you release the stone, you will see that it is going in the tangential direction. And I told you about tangential direction in the previous chapter as well. What is tangential direction? The direction which is perpendicular to the radius. So a straight line that meets the circle at one and only point is called tangent to the circle, and it is perpendicular to the radius at that very point. Okay. So what is centripetal force? So we have two forces. One is centripetal force and the other is centrifugal force. So let's read about the centripetal force. The change in the direction involves the change in velocity or acceleration. The force that causes this acceleration and keeps the body moving along the circular path is acting towards the center. This force is called centripetal. So basically centripetal force is center-seeking force, right? So for example, if two forces are acting on this object, one will act towards the center, one will act away from the center. The force which is acting towards the center is your centripetal force. Okay, so it is your centripetal force. Like in the previous example where we were revolving a stone with a thread, in that very motion centripetal force was acting. There was a force which was acting towards the center so that your stone keeps moving in the circular motion. So this is your centripetal force. Moving further. So the motion of the moon around the earth is due to the centripetal force. See, the moon is revolving around the earth. It is because of this centripetal force, the force which is acting towards the center. It is an attractive force, right? Like this. Centripetal force is acting towards the center. This is why your moon is not going on a tangential path. It is going on a circular path. So the centripetal force is provided by the force of attraction on the earth. If there was no such force, the moon would pursue a uniform straight line motion. Correct? If there was no centripetal force, then what will happen? There will be no attractive force towards the center, and your moon will rather prefer to go tangentially in a straight line motion. So let's think about this. A falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards an apple. Of course, have you ever seen that the earth is moving towards the apple? No, but the apple falls down, right? So let's figure out. So interaction between the apple and the earth. According to the third law of motion, the apple does attract the earth. But according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. So in the second law of motion, we have learned that force is equals to mass into acceleration. So which implies acceleration is equals to force by mass. This means an acceleration is inversely related to mass, correct? So mass of an apple is negligibly small compared to the mass of the earth. So we do not see the earth moving towards the apple. So let's know about universal law of gravitation. So gravitational force. Newton, Sir Isaac Newton, concluded that not only does the earth attract an apple and the moon, but all objects in the universe attract each other. The force of attraction between objects is called gravitational force. So it is not just the earth, but all the objects attract each other. So this is known as gravitational force. So universal law of gravitation, what does that state? It states that every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distances between them. So it is saying that force is proportional to the product of their masses. For example, if we have two objects and a mass of the first object is m, capital M, and mass of the another object is small m, so your force is proportional to product of their masses. And it is inversely proportional to the square of their distances, right? So this is what your universal law of gravitation states. So what does that mean? That force is proportional to product of their masses and inversely proportional to the square of distance between them. We can relate it like this. So what can we say? We say that force is proportional to mm by r square. So we can say that force is equals to gmm by r square, where g is your some constant, correct? Because because this is your proportionality and we can add one constant to equate it, right? So the force is along the line joining the centers of the two objects. For example, these two are objects, capital M, mass m, and distance between them is r, suppose. So this will be your force. So universal law of attraction is also called Newton's law of gravitation. Since gravity is given by Newton's earth, we say that universal law of attraction is also called Newton's law of gravitation. So formulation of universal law. According to universal law of gravitation, the force between two objects is directly proportional to the product of their masses and the force is inversely proportional to the square of the distances between them. So let's do the formulation. This is what I just told you, right? This is how it comes. This is right. So we took the distance as r, they are taking as d. Your force is proportional to mm by r square. So your force is equals to gmm by r square. If you take the distance as d, it will be gmm by d square. So what is your g? G is your gravitation, universal gravitation constant. And what does it come out to be? F into r square upon mm, correct? This is what is written, right? So G is your constant of proportionality and is called universal gravitation constant. Okay, G is your constant, the name given to the constant. So let's calculate the unit and value of G. It is very simple since we know the formula now. So we know that force is equals to gmm by r square, right? So what is your G? Which implies your G is equals to Fr square by mm. So now, as we have previously also done, that whenever we want to find the unit of any constant, we put the units of other elements in the formula. What is the unit of force? It is Newton. What is the unit of distance? It is meter, and since it is distance square, so it will be meter square. And what is the unit of mass? Kg. Again, what is the unit of mass? Kg, right? So this comes out that the unit of G will be Newton meter square per kg square. So this is your unit of G, right? So this is a Newton meter square per kg square. So the value of G was found out by Henry Cavendish, this scientist, by using a sensitive balance. So what is the acceptable value of G? And when we calculate the value of G, so it comes out to be 6.673 into 10 to the power minus 11 Newton meter square per kg square when we calculate the value for Earth, right? So let's do a small question with you all. So let's read the question. The mass of the Earth is 6 into 10 to the power 24 kg and that of the Moon is 7.4 into 10 to the power 22 kg. So your mass of Earth is given to be, mass of first object is your 6 into 10 to the power 24 kgs. And the mass of your second object, small m, is your 7.4 into 10 to the power 22 kg. So for it says that the distance between the Earth and the Moon is 3.84 into 10 to the power 5 kilometers. Your D is 3.84 into 10 to the power 5 kilometers. So you have to calculate the force. We know the formula for force and we have everything. And take G is equals to 6.7 into 10 to the power minus 11 Newton meter square per kg square. This is your value of gravitational constant. So this is given in this question, but you must remember this, okay? So what is your formula for force? Force is equals to gmm upon d square, correct? So what is your force? Force is equals to, what is your G? 6.7 into 10 to the power minus 11 into, what is m? 6 into 10 to the power 24 into small m, 7.4 into 10 to the power 22 upon d square. D square is 3.84 into 10 to the power 5 whole square, correct? So when you calculate all this, it comes out to be 2.02 into 10 to the power 20 Newton, because the unit of force is Newtons. Don't forget to write this. So just you have to plug in the values in the formula. This is your formula and you will directly get the answer and calculate. So state the universal law of gravitation. So we have already stated it in the previous slides. So yeah, you can do this question. Next question. Write the formula to find the magnitude of gravitational force between the Earth and an object on the surface of the Earth. So we have already derived the formula. What is the magnitude of the gravitational force is? It is gmm by r square, right? So now what is the radius of the Earth, like distance of the Earth? And we need masses. So this is the formula which will be used to calculate the magnitude of gravitational force. So moving further. So importance of universal law. So what is the importance of universal law? Why are we studying it? So universal law of gravitation successfully explained several phenomena. What all does that explain? It explains the attractive force, like the force that binds us to Earth. It explained that. Why the apple fall down. It explained the motion of the moon around the Earth. It explained the motion of the planets around the sun and the tides due to the moon and the sun. So now let's talk about free fall and weightlessness. As the name suggests, free fall, that no velocity is given to it, it is just dropped. Free falls means Free fall or weightlessness means that something which is dropped. There is no velocity attached to it. It is just under a free fall, right? If something is dropped, then which force will act on it? Only gravity, that attractive force, right?
We often say that all objects are weightless in space, but that does not mean that there is no gravity. Let's take a look at this equation. This equation allows us to determine the gravitational pull on the surface of a planet. So let's see. We have big G. Big G is a constant, often referred to as Newton's constant, although actually it was determined 70 years after Isaac Newton's death by Harry Cavendish. Then we have big M. Big M is the mass of the Earth in kilograms. So that would be around 6 million kilograms. And big R is the average radius of the Earth in meters. That is about 6,370,000 meters. Introducing numbers, we determine small g as being equal to 9.81. And that can be expressed in newtons per kilogram. And it basically represents the amount of weight per kilogram of an object in that particular point in the gravitational field. Or we can also express it, and that's equivalent, as meters per square seconds. And that is the acceleration of a free-falling object in the gravitational field. You can make your own calculations for the International Space Station. Just add to the radius of the Earth the altitude of the ISS above the surface of the Earth, which is about 400,000 meters. If we do that, we get a value for small g roughly equal to 8.7. So on the surface of the Earth, we had 9.81, which is about 10% bigger. So the force of gravity, the pull of gravity here up on the International Space Station is indeed a little bit smaller, but not that much. So if there is the force of gravity up here, why am I floating? To explain that, we have to introduce the concept of free fall. So let's use this model of the Earth. And let's enlist the help of a friend, Paxi. You might know her. Paxi, hello Paxi. She's with me on the International Space Station. So for the purpose of our little demonstration, let's assume that Paxi is the space station. We have calculated a short time ago that the gravitational pull of the Earth up here at 400 kilometers altitude is only about 10% smaller than it is on Earth. So if the Earth is attracting us, why don't we, Paxi, me, the entire space station, why don't we just crash onto the Earth? Well, the thing is that we also have a huge velocity vector. We are flying at about 8 kilometers per second. And that means that if there wasn't the gravitational pull of the Earth, we would just keep going straight at that velocity. However, because the Earth does attract us, the Earth curves our trajectory so that we keep flying around it. In a way, we can say that our trajectory, the curvature of our trajectory, matches the curvature of the Earth. So Paxi, me, the space station, we are all constantly falling towards Earth. But in a way, the surface of the Earth is curving away from us so that we never crash onto it. Objects of different mass, like let's say me and the knitting needle, are accelerated equally in a gravitational field in the absence of air resistance.
Free fall and acceleration due to gravity. Whenever objects fall towards the Earth under this force alone, the objects are in free fall. Right? So whenever no external force is applied, we say that the objects are in free fall. So while falling, there is no change in the direction of the motion of the objects, but due to the Earth's attraction, there will be a change in the magnitude of the velocity. So any change in velocity involves acceleration. Whenever an object falls towards the earth, an acceleration is involved. This acceleration is due to Earth's gravitational force. Therefore, this acceleration is called acceleration due to gravity, and we just know that we denote it with small g. It is denoted by g. The unit of the g is the same as that of acceleration. And what was the unit of your acceleration? It was meter per second square, because acceleration is a force upon mass. The unit of force is Newton. The unit of mass is kg. One is this unit. This was your acceleration, right? And one more unit of acceleration was meter per second square. And how did we derive that? With the help of the formula. Acceleration is a rate of change of velocity. So what is your unit of velocity? It is seconds. And what is your, it is meter per second, yeah. Velocity, meter per second. And what is your unit of time? Seconds. So it is your meter per second square. So this is how we derive the unit of acceleration, right? SI unit. And G is a type of acceleration. It is acceleration due to gravity. So the unit of G is same as that of acceleration, that is meter per second square. So free fall and acceleration due to gravity. See, can you see the astronaut on a free fall? So there is only one force acting on him in this video, which is the force of gravity. So magnitude of gravitational force. The gravitational force will be equal to the product of mass and acceleration due to the gravitational force. Force, the same thing which we have studied earlier also. Force is directly proportional to the product of masses, and force is inversely proportional to the square of distances between them. And then we derived this, right? Force is equals to gmm by d square, if d is the distance between them, right? So also using second law of motion, what did we study in the second law of motion? In the second law of motion, we studied that force is equals to mass into acceleration, correct? And if we are talking about the earth and the gravitational force, what will be our acceleration? It will be acceleration due to gravity. It will be equal to g. So our force will become mass into gravity, acceleration due to gravity, I mean, right? So, and force is also equal to g mm by d square, right? This is 1, this is 2. Both of these are forces, we can equate them, correct? So we'll just equate them. mg is equals to g mm by d square. What do we get from here? We get that g is equals to g capital M by d square, right? And if your distance is equal to the radius of earth, then what does that become? G is equals to capital G M upon capital R square, if R, where R is your radius of earth, right? Isn't that simple? Why did we use G here in our formula mg? Because G is your acceleration due to gravity, correct? So variation of G. So, you know, G is not same everywhere. It varies. So, let's know about it. Earth is not a perfect sphere. As the radius of the Earth increases from the poles to the equator, the value of G becomes greater at poles than at the equator. If this is your equator line, the 0 degree line, and these are your poles, okay? So G will be greater at poles or at equator? So G will be greater at poles. G is much greater at poles than at equator. Why so? Because the radius of the earth increases, no? When we go from poles to equator. So that's why your G increases as you go from pole to equator, right? So objects far from the earth, the acceleration due to gravitational force of earth is given by G is equals to gm by d square, okay? So value of G. So gravitational constant G is equals to 6.7 into 10 to the power minus 11 Newton meter square per kg square. We've discussed it in the example which we did, right? So your force is equals to GMM by R square, and the value of G comes out to be roughly 6.7 into 10 to the power minus 11 Newton meter square per kg square. Don't forget the units, right? We derived it from the formula. So your mass of Earth is nearly equal to 6 into 10 to the power 24 kgs, and radius of Earth is nearly equal to 6.4 into 10 to the power 6 meters. So what is your small g acceleration due to gravity? We derived the formula is gm by d square. We have to do nothing but plug in the values. And what is your d square here? It is your r square. If we are talking about the Earth, correct? Radius of Earth is 6.4 into 10 to the power 6, right? So what will it become? We'll just plug in the values of g, m and r in our formula. So d square is nothing but your r square, right? Because we're talking about the radius of the Earth, right? We are calculating for Earth. So g is like 6.7 into 10 to the power minus 11 into capital M is 6 into 10 to the power 24 upon what is your r square? 6.4 into 10 to the power 6 meters square. And this, when you calculate this, you can calculate it with the help of calculator right now, right? And it comes out to be, or you can also calculate it manually. Try, and you'll see that it comes out to be 9.8 meter per second square. And this is the value which we'll be using in the calculation, the acceleration due to gravity, okay? 9.8 meter per second square. How is it derived? It is derived using the formula G is equals to gm by r square, okay? So acceleration due to gravity of the Earth is nothing but 9.8 meter per second square. Correct? This is very interesting. You can, if something is dropping, you can just calculate its speed and everything, because the acceleration is g, right? So motion of the objects under the influence of gravity. So which one of the following would reach the ground first in the absence of air? You tell me. This is your basketball. You have basketball and you have tennis ball. So if you just drop both of them, just drop. If you're dropping, so then its initial velocity will be 0. Here also 0. In the case of for dropping, our initial velocity is always 0. We are not giving it any speed or velocity, right? We are just having a free fall. Okay, so you tell. So which one of them has greater mass? Tennis ball or basketball? Of course, basketball has greater mass than tennis ball, correct? So if your air is absent, then what will happen? So you will say that basketball is heavier and it will reach faster, but you are wrong, because we are talking about absence of air. Do you remember that video which we just saw, in which we had one straw and one taxi, and both of them fall at this, like they reach the ground at the same time, because in the absence of air there is no resistance. So what will happen in the absence of air? Both tennis ball and your basketball will reach the ground at the same time, correct? Will reach at the same time. So if you say that, basketball should reach first or tennis ball should reach first, you're wrong, because in the absence of air, no resistance is provided. And what will happen? Both will reach together. So motion of objects under the influence of gravity.
Objects of different mass, like let's say me and the knitting needle, are accelerated equally in a gravitational field in the absence of air resistance. This was demonstrated nicely on the Moon in 1971, when Apollo 15 commander David Scott dropped a feather and a hammer on the Moon, and they were both equally accelerated towards the center of the Moon and hit the surface at the same time. Also, if we could set up a controlled experiment and had a long time to observe, we would notice that all objects with mass are attracted to each other. This knitting needle to me and me to the knitting needle. How long do you think, roughly, it would take for these two objects to come together due to their gravitational attraction? So, despite objects in free fall being weightless, their mass does have an effect. That effect is called inertia.
As the object experiences acceleration during the free fall, and it is independent of its mass. As g is constant near the earth, all the equations of this thing that the object experiences acceleration during free fall, it is independent of mass. Like we saw that both the masses were different, right? And there was no air, so both fall at the same time. So yeah. So an object during the free fall and is independent of its mass. During the free fall, when there is free fall, then no matter if an object is heavy or an object is very light, they are independent of its masses. They are not dependent on mass, right? At what time they'll reach, it is independent of mass. Free fall is independent of mass because we haven't given it any velocity. It is the case of dropping, okay? As g is constant near the earth, all the equations of the uniformly accelerated motion of objects become valid with acceleration a replaced by g. So do you remember the three equations of motion which we did? What were they? Yes, I know you remember. Just quickly recap. One was v is equals to u plus at. Then s is equals to ut plus half at square. And 2as is equals to v square minus u square. That's great that you know these. Great, cool. So, if you're talking about g, it is also a type of acceleration, right? It is acceleration due to gravity. So, if we plug in g in this formula, we can replace g with a, right? When our acceleration is equal to acceleration due to gravity, when our acceleration is equal to g, then what will v become? It will become v is equals to u plus gt. And our second equation will become s is equals to ut plus half gt square. And our third equation will become 2gs is equals to v square minus u square. So these are three equations of motions when we are talking about a free fall, because our acceleration is equal to our acceleration due to gravity. Okay. So question 1. A car falls off a ledge and drops to the ground in 0.5 seconds. So firstly, the car is falling off a ledge and it drops to the ground. So car is falling off a ledge and it drops to the ground in 0.5 seconds. If the car is dropping, what does that mean? That it doesn't have any initial speed, okay? So in the case of dropping, our initial velocity is 0. Let g is equals to 10. And if you're talking about free fall and there is no initial velocity, right? So under free fall, we know one acceleration is always working. That is our acceleration due to gravity. And what was its value? Its value is roughly 9.8 meter per second square. But for the purpose of calculation, and also it is given in the question that let g is equals to 10 meter per second square. Okay. So we have g is equals to 10 meter per second square. What is its speed on striking the ground? And which equation are we going to use? We need to find the final speed. Isn't that easy? We know which equation of motion? First equation, we know v is equals to u plus at. And if our a is equal to our acceleration due to gravity, so it is u plus gt. So v is equals to 0 plus 10 into 0.5. And this is equals to 5 meter per second. So what will be our final velocity? It will be, what is its speed on striking the ground? It will be 5 meter per second. Next question. What is the average speed during the 0.5 seconds? What is the average speed? And what is average speed? Average speed is total distance upon total time taken. So firstly, to calculate this, we need total distance. And how will we find out that? With the help of the second equation of motion, which is S is equals to ut plus half gt square, correct? So we'll plug in the values ut, it becomes 0 plus half gt square, 0.5 square, correct? So your distance is equal to 125 into 25, 0.25, and this is equals to 1.25 meters. And now what are we supposed to do to calculate the average speed? Total distance is 1.25 and total time is your 0.5 seconds. We'll just calculate this and we'll get the average speed. These are just basic formulas which you are supposed to use, right? So your average speed is 1.25 upon 0.5. So yeah, our average speed is equals to 1.25 upon 0.5. So let's calculate this. What is our average speed? Is equals to 0.5 meter per second. 1 second. It's 125, right? 1.25 upon 0.5. 1.25 upon 0.5 into 10 into 100. It is 125 upon 50, correct? So it is your 2.5 meter per second. What else are we supposed to calculate? So one more thing, how high is the ledge from the ground? Okay, so we have to calculate the height. So how can we calculate the height? You people tell me. From the third equation of motion. Or we can also use the second equation, right? We know S is equals to ut plus half gt square. And what is your S? It is your height, right? That is the distance covered, okay? So h is equals to u was your 0. So this term becomes 0 plus half. G is your 10. And what is your time? Time is your 0.5 square. And this comes out to be 5 into 0.5 square is 0.25 equals to 1.25 meters. So let's continue. So let's do one more question. An object is thrown vertically upwards. Object is thrown vertically upwards and rises to a height of 10 meters. Calculate the velocity with which the object was thrown. So if something is thrown, it should have some initial velocity, right? So we have to calculate this initial velocity. Okay. And it rises to the height of 10 meters. Now you need to think one thing. When the object is thrown upward and it attains a maximum height, right? At that very time, its final velocity must be 0. If, like something you throw upward, after a certain point, it comes down, right? So at that maximum point, if it is given that it rises to a height of 10 meters, what does that mean? That after rising to 10 meters, it will come down. So at this point, what will be your final velocity? It has to be 0, correct? So calculate the velocity and with which the object was thrown upwards. Okay, no problem. So we have v is equals to 0. We have to find out q. And we have g is equals to 10 meter per second square, which we take for calculation. Otherwise, g is 9.8 meter per second square. And we have, what else do we have? And we need to calculate the velocity, correct? So, we also have the distance, the height, correct? H. we have that h is equals to 10 meters. So which equation can we directly use? Think of this. The equation which involves v, u, g, h. We just have one such equation if we want to directly apply. What is that? 2as, so 2gh, because your s is equal to h and a equal to g, right? V square minus u square. So 2, 10, and what is your h? 10 is equals to 0 square minus u square. What is your u square? You need to calculate u square, correct? Okay, so one thing you need to keep in mind. Okay, so you see that your gravity is always acting in the downward direction. Okay, gravity is always acting in the downward direction. But what is the motion of your object? It wants to go in the upward direction. So what will, so these are opposite direction. So what will be the sign of g? It will be minus 10. Okay, minus 10. So g is your, not h, your g will be minus 10. Correct. So your 200 is equals to minus 200 minus u square. U is equals to root 200 meter per second. You can just calculate this. Correct. So with this you will get your u. So here we are using g as minus 10. But since it is not mentioned in the question, you can also calculate with the help of g is equals to 9.8, right? And don't forget to put the minus sign. Okay, so then what will be your what's that? Velocity? We'll plug in 10 ki jagah, in place of 10, we'll put minus 9.8, okay? Then also, with this also we can calculate. There would be a slight difference, okay? So, the time taken by the object to reach the highest point. You people tell me which formula are you gonna use for this? So, we can use both the formulas. Either we can use the formula s is equals to ut plus half at square, right? H is equals to ut plus half gt square. Either we can use this formula. We know the height, that is 10 meter. We know the u, we just calculated. We know the time. No, we just have to find this time. Only one variable. We know g, correct? So we can find out t with the help of this equation. Also, we can use our equation, third equation of motion, 2gs is equals to v square minus u square, right? From here, we got the u. And now we can simply use our first equation, v is equals to u plus gt. We have v, we have u, we have g. We just have to find out t. So, this is like a very beautiful concept that you can use any equation, either first or second or third, like alternately, find the value of t, then plug in here or, So, this is great. You can, for practice, you can calculate by n number of methods, which are possible. Okay. So, this is it. I want you all to calculate this on your own. And if you have any doubts, ask. It's really simple. You just have to plug in the values. Okay. This is the homework for today. If you have any doubts, you can discuss in the next lecture. So, what do you mean by free fall? We have watched so many videos on free fall. Correct. And I'm sure you are clear with free fall now. So, free fall is a term which is used to describe an object which is under the force of gravity. Which is under the force of gravity and no other external force is acting on it. Correct. For instance, if a ball is, for example, a ball is dropped. Right. In that very case, your initial velocity, anything, is under free fall, just dropping, just free fall. The things. Okay. So, what do you mean by acceleration due to gravity? First thing is, it is our small g. And how will we define it? We have read it so extensively. I hope you all can answer this. Right. So, what is acceleration due to gravity? It is the acceleration gained by the object due to the attractive force between the two objects, correct? So, it is due to the attractive gravitational force, right? So, for example, when we talk about free fall, So then also there is an attractive force. For example, our Newton's are give no that apple falls down. So there is an attractive force. So the acceleration gained during this process, the change in velocity due to the attractive force of gravitation is your acceleration due to gravity. Okay. So thank you everyone, and we'll meet in the next class with more about gravitation and mass and weight. So yeah, we'll discuss in detail about this in the further chapter. So most of you think that mass and weight is the same thing, but in this chapter we'll know that these are not same. These are two different things. Mass is different and weight is different. And when you say that my weight is 10 kg, my weight is 50 kgs or 60 kgs, that time you're not actually telling your weight, you're telling your mass. So this is very interesting topic, and we'll definitely learn about this in detail in the next class. So bye bye, have fun, take care, and if you have any doubts, feel free to ask. And love physics. Bye bye.